Hi everyone, my name is Hassan Sheikh and we will be presenting our anti-scam website detection machine learning model. In this era of internet and technology, internet usage is very common to use across all ages for many daily usages like research, social media, purchasing goods, entertainment, learning, and many more usages. Because of this, we have seen a wide increase in fraudulent and fishy websites where the site owner or attacker attempts to gain sensitive information from the user for his or her own commercial benefit. Younger kids and elderly are especially vulnerable because there are limited safety measures in place to help them differentiate scam versus fishy websites. So this has attracted the interest of many to apply machine learning modeling to automatically identify which websites are scam or not based on a particular website's characteristics and features to create safety measures of using the internet. Scam detection has been around for a while now. The models that are in place are very beneficial and helpful, and we just hope to add to that safety net by discovering more red flags to identify scam websites. Even though an average young adult can tell something may or may not be a scam because some things are just too good to be true, many fraudulent websites are starting to look like legitimate sites. And this can be especially problematic for, again, the elderly and the younger kids who may not understand what the normal of the internet is. Consequently, in our project, we'll be using machine learning techniques to identify suspicious websites to protect ourselves from fraud and its negative consequences such as wrong information or purchasing from the wrong sites. We found a research study that was conducted on a large number of websites on the internet, which identified whether a website was scam or legitimate. The study had two variations of datasets, a small dataset with 58,645 websites and a large dataset of 88,647 websites. Each dataset has 111 features which can be divided into 6 different categories. The first category is the whole URL. This identifies the number of a specific attribute inside the whole URL of a website. For example, the number of period signs in any URL is a feature inside the dataset. The second category is the domain of the URL. This identifies the number of a specific attribute inside the domain of a URL. For example, google.com without any of the backslashes has 1 period in it. The third category is URL directory, and this identifies the number of specific attribute inside the directory of a website. The directory is where all the backslashes are, and you can go through different pages, and that's just specifically the backslashes. The fourth category is URL file name properties, and this identifies the number of a specific attribute inside the file name of a URL if it contains one. The fifth category is the URL parameter properties. This identifies the number of a specific attribute inside the parameter of a URL if it contains one. For example, if one was searching for the ranking of LeBron James in 2016 for the Lakers or for the Cavaliers, then that would be a parameter inside the URL, and so this is a specific attribute inside there. And the last one is the URL of resolving data and external metrics. This identifies the features that cannot directly be seen in a website's URL. For example, the number of redirects the website goes through when clicked is a feature under this category. Taking in all 111 features as a Boolean value 01 was given to identify if a website was scam or a legitimate site. For our data analysis, we used a larger dataset because a larger dataset was more appropriate to the actual number of websites on the internet.
As mentioned before, the data contains 111 features. Only a small number of these features are important, so we performed feature selection to isolate them. Our group implemented 2 methods to reduce the dataset: random forest and feature permutations. So the random forest builds 100 decision trees. For each tree, all the data is placed at the root node. A feature is randomly selected, and the data is split depending on its value for that feature. Since we didn't include any hyperparameters to reduce the splitting, the tree grows until all the leaves are homogeneous. Unfortunately, this model is prone to overfitting our data. Many of the features have unique values, which preemptively makes them seem important. This trouble is addressed in feature permutations. Feature permutations builds trees just like a random forest. The difference is that feature permutations begin with all the features and calculates a model score. As a feature is randomly removed, the model score is re-evaluated. Through this backwards process, the importance of a feature avoids high cardinality bias since it reflects its importance to the model as a whole, not its intrinsic predictive value. Our group constructed 2 feature permutation models, one with no minimum number of points in a leaf and the other with a 5-point minimum. The 5 is meant to reduce overfitting. For each model, the importances of the features were calculated 3 times based on 3 different metrics: accuracy, precision, and recall. This resulted in 6 different feature permutation models. We plotted the importances of the features versus number of features for all 7 models. Several of the models begin to plateau around 4 features and at around an acceptable importance level. Therefore, we proceeded to shrink our data to only 4 features. Although all models shared the most important 2 features, Random Forest differed from the 6 permutation models concerning the next 2 important features. And this graph here shows all of our training data plotted against the 2 most important features. As can be seen, it is practically impossible to effectively separate all the data based on just 2 features. This also justifies us selecting 4 features.
Moving on, we used the Gaussian naive Bayes, logistic regression, and random forest models. First, the Gaussian naive Bayes. This one was based on Bayes' theorem, which assumes that features are conditionally independent given the class label. It's less prone to overfitting because of this simple assumption, and is also very computationally efficient. However, it may not capture complete relationships between the features, which is what we saw. We also used the logistic regression model. This one uses soft assignment and the sigmoid function, as you can see here, and it gives values between 0 and 1. It also has a 0.5 threshold value. It assumes linear relationship between the input features and the log odds of the outcome. It's great with binary classification. Lastly, we also used the random forest model. It combines multiple decision trees to reduce overfitting and improve computation speed. Each decision tree is built on a random subset of the data, and is highly effective for handling high-dimensional data, nonlinear relationships, and noisy features.
And now to our results. To determine the effectiveness of our prediction and feature selection models, we calculated the following 4 metrics for each prediction model on each of our 2 reduced datasets. Recall that one reduced dataset came from the random forest, and the other came from feature permutations. So out of the 4 metrics, F1 is the main focus. Because with scam website detection, it's safer and more acceptable to label a safe website as scam than label a scam website as safe. Therefore, the desired evaluation metric should try to minimize false negatives and also maximize true positives. So at first glance, recall seems to fit this description. Unfortunately, recall doesn't consider false positives at all. A model which simply labels all websites as scam will have a perfect recall of 1. Therefore, a relative balance between false negatives and false positives is necessary. False positives is taken into consideration through precision, and F1, which balances recall and precision, is therefore the best measure. So the following 2 graphs show the results for our Gaussian naive Bayes and logistic regression prediction models. The large disparity in performance between the training and testing data for the forest reduced dataset seems to support our previous concern of random forest feature selection overfitting the data due to high cardinality bias. This overfitting isn't present with the feature permutations reduced dataset. However, the F1 scores of about 0.7 and 0.8 respectively can be better. So this graph shows our results for the random forest prediction model. And so all the testing data metrics through the feature permutations testing reduced data are much higher. They're all around 0.9, as can be seen here, and the F1 score in particular is 0.9135 or 91.35%. So overall, from this project, our group learned that random forests are effective prediction models for scam website detection. Additionally, feature permutations is very fitting to extract the most important features. From our reduced dataset, the most important features are the directory length, the number of days the domain has been active, the number of periods or dots in the domain, and the length of the entire URL. As can be seen, all these features only have to do with the URL of a website, and that is because our dataset only included features concerning the URL of a website. In the future, our group can extend this further by exploring other features of websites, including the number of ads or any citation information, etc. But for now, based on just the URL of a website, people who wish to avoid scam websites should watch out for long URLs, especially ones with lots of periods. Thank you.